The company I'm recommending has a flywheel technology that will suck up surplus energy when demand falls short of supply and will return that energy to the grid when the reverse happens. It's simple. Imagine standing in front of two giant wheels, each weighing a ton, spinning with power inside a quiet lab. They turn without fuel, without smoke, and without the roar you expect from machines that hold this much energy. Today, we entered the Power Lab to explore a device built in 2017 and 2018 known as Model 30. It is the only counter-rotating version still running, and it was designed to prove that magnetic propulsion could work on a ship with about a 7% lift change. Simple on the surface, this machine stores, controls, and delivers clean, reliable mechanical power. The heart of the machine? Two giant flywheels. At the center of Model 30 are two massive flywheels. In the lab, they have friendly names, Carol and Joyce, but there is nothing small about them. Each wheel weighs around 2,000 pounds. Each one sits on its own shaft and drive system, and each spins completely independent of the other. Between them sit two common aluminum lens plates, one near each wheel. These plates help form the paired permanent magnetic field that links the two sides of the machine. When the wheels spin, you can actually see flashes of the permanent magnets as they sweep into that field. It is a subtle effect, but up close, it feels almost alive. The computer that handles control for the engine works to keep the two flywheels within about 10 revolutions per minute of each other. This keeps the system balanced and smooth. RPM readouts on the front of the machine show the speed of each flywheel as they climb from idle toward operating speed. Even at moderate speeds like 60 or 70 RPM, those 48-inch discs hold a surprising amount of stored energy. If you plug their size, mass, and speed into any basic flywheel energy calculator, you will see how much kinetic energy is locked inside that spinning steel. It is important to remember that the flywheels do not generate electrical power by themselves. They are storage devices, not generators. Their job is to take mechanical input and hold it as kinetic energy. The alternator mounted behind them is what turns that stored motion into usable electrical output that can power real loads in the building. The alternator and the power path. Walk around to the back of the engine and you find the alternator train. It rides on a simple slide, so it can move a short distance, in or out. That motion may look minor, but it is the key to how the system controls power. When the alternator is pulled back, it disengages from the flywheel train, and the load on the wheels almost disappears, so they speed up. Push the alternator in by 20 or 25 millimeters, and it instantly begins to turn. As soon as it makes contact, it starts drawing energy from the flywheels. The alternator shaft has a 3-to-1 mechanical advantage. So, it spins 3 times faster than the main flywheels. Behind it sit two 18-in plates, each about 150 pounds, adding inertia that keeps rotation smooth and steady. This alternator is rated at 10 kilowatts, but the building limits what can be drawn. In normal use, the system produces around 3.5 kilowatts while staying within local limits. The alternator generates a C power which then passes through a rectifier and becomes DC for safety and code reasons. The system is capped at about 60 volts DC. From there, the power flows through a common charge controller into an inverter and finally into the battery storage bank. This single engine powers Quad 4 of the facility, which includes this room and nearby laboratory space. On a tour, you can see the engine running and also see which lights. Tools and systems are being supplied by power that began as motion inside these two spinning wheels. Control, monitoring, and lubrication. A system like this needs clean, reliable lubrication. Instead of dark, messy oil, the engine uses a PTFE-based fluid that stays clear and leaves no black residue. It keeps bearings and moving parts coated and protected, while also keeping the machine tidy, enough to act as a working showpiece. This matters because the engine is not hidden away. It is meant to be seen up close. For control and monitoring, the lab uses Borg-Warner software tied into the system. On screen, you can see how much control, voltage, and parasitic energy go into the device to keep it spinning and synchronized. Visitors can compare those numbers with the electrical output to see how much net energy the machine is delivering. The front panel displays RPM for each flywheel and for the alternator, so you can watch the numbers change in real time. When the alternator is slid out and the electrical load removed, The flywheels climb in speed because they are no longer pushing against a generator. When the alternator is pushed in and the load is reapplied, the speed drops as the system begins to push energy out to the charge controller, inverter, and storage system. It behaves like a mechanical governor that the operator adjusts simply by moving the alternator along its slide. Because the machine is open and accessible, people on tours can bring their own meters clamped to the output at safe points and see exactly what the system is doing under real load. Energy storage and performance in motion. The real magic of Model 30 lies in how it stores and releases energy. Each flywheel is 48 in diameter and weighs around a ton. Spinning all that mass turns the wheels into mechanical batteries. The faster they spin, the more energy they hold. Unlike chemical batteries, there are no cells to wear out or electrolytes to leak. All the energy is stored in motion. Under normal conditions, the lab runs this engine at modest speeds to follow building standards and stay within safety limits. Even so, the system can run the flywheels up toward 300 RPM if needed. In day-to-day operation, the alternator often turns around 175 RPM while charging the batteries or running loads. That is enough to keep Quad 4 energized. As demand changes, the operator can adjust how far the alternator is engaged, tuning the balance between stored energy and delivered power. This also makes the machine's behavior very visible. When the load is high, the flywheels slow as they give up stored energy. When the load is low or removed, they speed back up. You can literally watch the relationship between storage and output happen in front of you. For many visitors, this is the moment when the idea of kinetic energy stops being a textbook, abstract concept, and becomes something real and intuitive. Purpose, design, and public demonstration. Model 30 was never meant to be a sealed black box. It was built as a working demonstration platform for research and education. The guards around it can be removed for close filming. During tours, they are arranged so visitors can walk around the engine, see the lens plates, watch the magnets flash, and trace the path of power from the flywheels to the alternator and onto the batteries. The original design goal was ambitious. The team wanted to show that a magnetic propulsion unit like this could operate on a ship with only a small lift penalty, about 7%. The counter-rotating layout helps reduce net torque and makes the system more stable, which is important in a marine environment. This model stands today as the only counter-rotating unit still in place. A reminder of the early development work done in 2017 and 2018, the facility is about 52,000 square feet, with 4 engines planned to serve different sections of the building. This particular engine is tied to Quad 4, but it also plays a major role as a teaching tool. The lab designs and builds its own alternators and generators, including lay-flat and turbine alloy types. When you tour the Scottsdale facility, you can see not only Model 30 in operation, but also the equipment that converts its raw motion into clean, useful electricity. That helps visitors see that this is not a science fiction prop, but a practical system built from real manufacturable components, future potential, and real-world uses. Although this episode focuses on a single machine in a single lab, it hints at a broader idea. Large flywheel systems like this can act as energy buffers. They can smooth out fluctuations, store surplus power when production is high, and return that energy when demand rises. Model 30 shows how such a system can be rugged enough for industrial use, yet open enough for people to study. Because the flywheels use no fuel and create no direct emissions, they could pair well with renewable sources such as wind or solar. Excess energy during peak production could spin up the wheels, and the stored motion could later be tapped through alternators and inverters. Similar to the setup in this lab, the paired magnetic field, the counter-rotating design, and the mechanical advantage at the alternator all help make the system efficient and responsive. All this also points to engineering. You do not always need exotic materials or complex electronics to build useful technology. Sometimes you can take something as basic as a spinning wheel, combine it with smart control software and well-designed power electronics, and end up with a system that feels almost futuristic in how it handles energy. In the end, Model 30 is more than 2 heavy disks turning in a quiet room. It is a working example of how motion can become a controllable energy store. The paired magnetic field, the sliding alternator, the PTFE lubrication, and the computer control all serve one simple goal: to take mechanical energy in and send reliable electrical energy out. When you stand beside it on a tour and watch the RPM climb, you see power in one of its purest mechanical forms. Thanks for joining us in the Power Lab. We hope to see you in the next episode. Asterisk, thank you so much for watching, all the way to the end. If you enjoyed this deep dive, please smash that like button.